Hello, everyone. Welcome to Rational Science from Frankfurt, Germany. And today I'm here with my youngest son, Hans,
Hey.
my partner here, the manager, the boss. So today I gotta behave. Today we're gonna do a little review of the year, and then I'm gonna open the floor up for questions. Any questions, comments that you want to make, I'm going to try to answer them online, and Hans here is going to try to read them out for us. Okay, so let's get started here. Okay, one of the issues, I guess the primary issue we got today is the following. Here we go. Okay, and it's we're in the year 2020. Some people say that it's the lost year. We lost a lot of economics, and so yeah, I blotted you out. And the question is whether 2021 is the last year.
No, I already guessed it's 2023. That's my money.
Maybe that baby that's punching his card in there, he's gonna have a bout of progeria and maybe die in July or something. It's one of the things you want to consider. One of the things you want to ask questions about today. Okay, the extinction issue. And then there's another issue, and it's this one, and it's whether there was a civil war in 1860 to 1865, and the question is whether that was just the first civil war, like there was World War I, World War II. Are we going to have a Civil War I and Civil War II? Okay, in those days it was North against South. And today the map looks pretty much the same, except that maybe you could add some of the central states. You got East and West against the center, so to speak, center-south maybe. Okay, so maybe that's one of the things you got to consider. Will there be another civil war? If Trump stays or if he goes, whichever way, will there be a civil war? And if there is a civil war, will that fulfill the the prediction saying that this is the last year, 2021. And let me give you an idea here, what I'm referring to, in case there is a civil war. This is what you can expect. Okay, these are the ICBM silos in the United States, and you would have the Eastern and Western throwing against the middle. Some general here and another general over there. Okay, that's one possibility. It happened with the Romans. They hired the barbarians, some of the Visigoths and so on. And, eventually those were the ones who overthrew the Roman Empire, okay? So, yeah, it could happen. It could be internal. These are the naval bases the United States has. And here I think the East and West have an advantage because for some reason there are no ships in Kansas. I don't know why, but
There might be one.
Okay, and these are the Air Force bases. I'm sure they're not all there.
Wait,
So-
is this all need to know basis, or is this
Well,
top secret information you're passing out?
This is all CIA. I got it directly from the CIA, okay? And so you can see where the bases are. Maybe here they're pretty much equal, Could there be a war?
Who do you think would win, North,
Well, I think the
middle,
East,
or the edges?
No, I think the East and West again. Like if you look at the map here, where was it again? The Civil War here. You can see it was the maps look pretty much the same. It was always the North, East, and the West against the South, and now all we did was add the central states. Okay. So not much change. The only thing you got Lincoln versus Jeff Davis, and now you got Trump against Biden. Could that happen? Could that ever happen? Okay. Okay, so let's move on. Let me get back in here for a second. Okay, we're going to do a year in review. Essentially, I went through and looked at some of the videos that we put out this year. Okay, and here you can see it. Let me run it down. We ended last year with Ayn Rand, or Ayn Rand as some call her, and we started the year with her. The first week I think was the last we did with Ayn Rand, and my argument was she was not a philosopher. Why? Because philosophy is part of science, and it deals with explaining purposes and reasons, whereas physics deals with causes and mechanisms. Okay, so there's a difference there. And Ayn Rand, Wittgenstein, Kant, David Hume, Russell, all these people, none of them were philosophers. All they gave were opinions. Okay, they did work on language, but they did a lousy job with that, as far as I'm concerned. And we try to correct that here. Okay,
You mean definitions?
Yeah, definitions and so on, definitions primarily, but also analysis of words. They did not analyze it the way we would do it in science, in a scientific way. Okay, St. Thomas Aquinas, he was a mechanic, we found out. Why? He worked on cars or maybe stagecoaches? No. He's a mechanic because the mechanics borrowed just about everything from Aquinas, except that, they don't call them angels anymore, and they don't call them spirits, they call them particles. So it's these particles that can be at two places at once, just like Thomas Aquinas' angels were at two places at once. So he had already discovered the uncertainty principle, a long time ago. Science, not equal to religion. We analyzed science and said it's a little different than religion. Science is about explaining mechanism, especially in regards to physics, which is what we do here. And religion, what is religion? Well, religion is about opinions and beliefs. It's not about God. It's not about, you can believe in astrology. There's so many beliefs out there. You can believe in spirits and black magic. It doesn't have to necessarily be God. So, no, religion is not specifically about God. It's about beliefs. Everybody has a religion. Everybody has a system of beliefs.
I remember one good distinction we made between science and religion was that with science, it's more about presenting all the possible explanations for something, whereas religion was picking one. Like if someone asks how does magnetism work?
Choosing.
How does magnetism work? A scientist will give you the five theories on it, whereas the I don't want to call him religious person, but someone who just wants to sell you a belief will just give you one of them. Believe this. Believe the second one. This is the theory that it's true. Which theory is true is up to religion, whereas what are the theories? That one's science.
Yeah, truth, knowledge, persuading people, all that's part of religion. And everybody has a tendency to try to impose his beliefs, his religion on someone else. That's just human nature. And there's nothing wrong with that. It's just that we need to recognize that part of the presentation as being religion. Physics, science, philosophy, all those have to do with objective explanations so that you understand it, not so that you believe it. It's religion where they talk about knowledge and, I know God exists, and I know that space-time exists, and I know that a particle can be at two places at once. Okay, so when you've got a religion. It's when you don't know that you're doing fine. Okay, let's continue here. In the list, talked about the ether. What is ether? Well, it comes from the Greeks, and essentially it's a medium that supposedly is the one that vibrates or carries, or whichever way you want to phrase it, light. Okay, so it's the vibration of the ether that forms light. It's the vibration of these so-called particles that form the ether. So what is the ether? Well, the ether has always been the same thing. It's been particles, bunch of particles. That's the definition of ether. And a lot of people don't like that, but they never tell me what they think ether is. Okay, everybody has this different notion.
Do you mean it's like they say that it's an ocean of little balls?
No, well, that's what it is. But some people say, well, no, that's not it. But they never tell me what is. They always tell me what it ain't. And that's the problem. And mathematical physics today deals completely with an ether. We never got rid of the ether. Mathematical physics believes that space is an ether, that it's made of particles. That's quantum mechanics. General relativity has the same notion. The bread and butter, the building block of general relativity is the event. What is an event? It's a point in space-time. What is a point? Well, it's the sandbox, and a point is one of those grains. And that's what space-time is, a bunch of grains. Okay, so if you got a different idea what the ether is, well, you better write it down. And just to add on that, if you can define the ether, it's obviously not an object, because objects we point to, concepts we define. So if you say the ether is this and you define it, you can't say that you're going to vibrate it.
But hold on, if you say the ether is an ocean of little balls, then you could point to it technically.
No, because again, that's mereology. You can't. It's many particles.
Okay.
See,
Not
that's
one
the issue.
particle. Okay, I see.
An object is just standalone.
So
One
two,
object.
so two chairs isn't an object.
You got it.
Okay, got it.
It's a relation. Okay. Infinity. We dealt with that several weeks, and what are we talking about? Well, infinite is an adjective, and adjectives can only be used in physics to qualify objects, and all objects are finite. So to say that it's an infinite finite, it's an oxymoron. It's a self-contradiction. What they've done with this adjective, they turned it into a noun. And when they don't want to answer a question, or they can't answer a question, they send you all the way to infinity and say, why don't you go to infinity? Okay, infinity is that place where they answer questions. So go out there and find them. Space, vacuum, nothing. They are synonyms. No one has ever defined it. Everybody thinks of space as a physical object. And the way we do it in physics is, if you think space is a physical object, point to it. That means you have to show me the shape. And if you show me the shape, you got to show me the contrast. What gives it shape? What it contrasts against? Okay, and so you got to identify that medium as well.
I guess we're talking matter contrasts space, but the edges of space, we don't know where it is.
Yeah, but that's the point. If it's an object, you got to have this God's view, this bird's eye view, and say, look, that's space over there. Okay, tell me what's the thing that gives it shape? What's on the outside of it? And of course, that's a question no one can answer. And that's why mathematical physics has a standard answer to that question, and it's that it's an unscientific question. Because we can't prove its existence. What's outside of it?
I mean, when they draw a curved space, they don't talk about what's above the curved space. If space is a canvas going down, what's the stuff on top of it?
Not only that, when you see the general relativity space-time fishnet, I want to know what the black stuff that gives shape to each one of those strings is, and that's the one that they have trouble identifying always. Okay, and that's why they say, well, it's an unscientific question. Because obviously it's a conceptual issue. This is not a question of actually bringing space to you. It's a conceptual. I don't have to. I can imagine it. Just draw it, and I can imagine it. And what the problem is, you can't imagine it because you can't imagine what's outside of space, giving shape to space. If it's made out of particles, what's the stuff that's on the outside where the particles end?
Space number 2.
I guess.
Extra space.
Yeah. Okay. So we have a problem with space, and that's a problem in mathematical physics in general. The dimensions of mathematics have nothing to do with dimensions, length, width, and height. What they have in mathematical physics is number lines. And so one of the problems there is that time has been called a dimension when it's really a number line. Time has no direction, which is what number lines have, and it has magnitude and no direction, which is the opposite of what a dimension is. A dimension doesn't have magnitude, but it does have direction. And the other property of dimensions, real dimensions, physical dimensions, is that they're orthogonally to each other. In other words, they have orthogonality, perpendicularity with respect to each other.
Well, usually when a dimension is brought up, it has a magnitude, isn't it?
No,
like
that's as soon as you put a magnitude, you're talking about a number line. Because if it's got magnitude, you can't put magnitude to direction.
You can't say 5 centimeters.
5 is pointing in that direction. 4, 5, 6, 7 are pointing in that direction. Yeah. That's what you can't say. I mean,
you can't?
No, 4, 5, 6, 7 are directionless. That's why a number line, they always put an arrow and people say, okay, I understand, it's pointing that direction. No, number lines don't point in any direction. You can point them in any direction you want, or you can put the 4 over here, the 5 over there, and the 6 over in another place. It's not on a number line. It could be on a number curve for all we know. Okay, there's no direction to numbers. And that's a serious problem in mathematics because they do tend to, include it as part of physics. They want to show that the math represents physics when it doesn't. Okay, math and physics will never meet. Okay, we did quite a bit, in fact, throughout the year on quantum mechanics. It's entirely irrational. It's completely religion. Why? Because they have an irrational atom. Okay, what's the problem with the atom? Well, the atom is, we can't explain why the electron bead does not fall to the nucleus or leave the atom spontaneously. Why do you need to ionize, in other words, with some kind of external force? Why do you need to ionize an atom, pull its electron out? What holds it in its orbit to begin with? That's the issue. Why doesn't it fall to the nucleus? Why doesn't it fly away? Same with the Earth, by the way. Why doesn't it fall to the sun? Why doesn't it fly out of the solar system? Same issues in both cases. No one can explain what keeps those things at a distance at the same place. Orbiting in the same place all the time.
I heard there's ropes to tie them together.
The particle of quantum is not a particle. It's not a corpuscle. It's not a grain of dust. What is a particle? A particle is a number. What they're doing is accelerating and smashing quantities, amounts, number 5s and against number 10s or whatever. Virtual particles, that's magic. That's black magic. The particles just come in from the void. You have a black particle. Black particle comes against the white particle and turns into a no particle. Okay, or a black ball with white ball turn into no ball, and then the no ball can separate into black ball and white ball. What the hell is this?
So you reject the notion of matter coming out of nothing and matter turning into nothing.
Yeah, what they've done is they cannot explain certain aspects, especially of what happens in this subatomic microscopic world. So what do they say? They say, well, we cannot account for the energy. There's got to be a conservation of energy. Second law of thermodynamics, okay? So there's got to be a conservation of energy. They can't justify what they see in the chamber. They say, oh, we know. It came out of the vacuum inside the chamber. That's where the extra energy came. What do you mean the energy? Well, it's these particles, you see, and what is a particle? It's just pure energy. It's a quantum of energy, an amount of energy. And this energy now is in the equation. We say, okay, we can put that 5 extra kilo electron volts or whatever inside the equation. We're okay. Now we've got the conservation of energy. But then the explanation is the problem. Where did it come from? And they say, well, it came from the vacuum. Because, see, the vacuum, we know it's got seething energy. That's what the vacuum is, which is what? Particles, particles and antiparticles, which combine to form nothing, which is made out of particles. I hope you got all that, right? So we had a test on Friday. Okay?
Well, starting to get good questions for after the recap.
Yeah. So keep the...
we can scroll here anyway.
We're going to scroll later on and look at the questions, okay? Anyways, let me continue here, okay? Entanglement, how a particle affects another one at a distance. They can't explain that with particles. And so entanglement is just magic. Superposition, 2 particles at the same place. Decoherence, particle at 2 places at once, etc. So they invented all these principles. The principle of complementarity, of uncertainty, the exclusion principle. They've got all these principles that form the foundations of quantum mechanics. And all these principles are irrational. I always like to say the uncertainty principle, which is also known as indeterminacy. What is it? It says that when the ball moves, it doesn't stand still, and when the ball stands still, it doesn't move.
That's deep.
That's what Heisenberg.
That's deep. Yeah.
He demonstrated that mathematically, so it's proven. Okay, so believe it. They invented that. They invented the Higgs, which is another great particle. It's the particle of mass. Okay, it's like the particle of weight. Okay, if you can figure that one out. And then the graviton, they're still looking for it. They've been looking for it for 500 years, and they're going to continue. Number up here, yeah. General relativity also entirely irrational. Why? They have black holes, wormholes. I love the wormholes. They go right through space, which is nothing, and end up in another universe, which is part of ours.
What?
Dark matter, they can't explain the galaxy rotation problem, why the stars on the outside of a galaxy travel faster than the ones on the inside. It's like saying that Pluto can travel faster than Mercury. And you say, well, that's counterintuitive. Yeah, it is. And that's what a galaxy does. So how do you explain it with galaxies? Well, they sprinkled all these dark kilograms on the outskirts of the perimeter of a galaxy, and they say, see, we fixed it. Well, you fixed it mathematically. The question is, does that make sense physically? I mean, why isn't this dark matter between the Earth and the Moon? And if we sprinkled it there, it would upset completely Newton and Einstein, both of them. Both of them would be wrong. And Mond, the modified Newtonian what's his name, Millstrom invented. So it would have upset all the equations. Nothing would work if we sprinkled each one of these grains of dark matter, dark kilograms as I call them, and they weigh tons, and they're conveniently invisible, that sort of thing. So yeah, that's magic. All that is magic. Holographic universe, just nonsense that string theory needs. Big Bang creationism means that the universe started from nothing. Matter was created out of nothing. And, I just want to know the mechanism. As soon as you explain the mechanism, God will be listening together with me, because not even God can do that, okay? Nebular hypothesis, again, it's okay for the sun. I have no problem with the sun.
What's the nebular hypothesis?
It means that there's this cloud of, let me put ourselves in there for a second. It's this cloud of gas, right? Gas and dust and matter, etc., probably spat out by a supernova or a nova that happened before that. Okay, so it sprinkles all this gas, all this matter in a region of the space, you could say, or versus other matter.
Radially, I guess. And
what happens is it begins to spin. There's so much gas, so much matter that it begins to spin. And just like a skater, pulling his arms inwards, this mass of gas and particles rotates and comes together gravitationally also, and forms what eventually is going to be the sun. All this mass, all this matter condenses essentially, and at some point gravitation becomes stronger and stronger and stronger until finally it ignites and turns into a star. No problem there. That mechanism is not, I cannot imagine how the Earth came out of that mechanism. Okay, in other words, what you have these little gas clouds supposedly orbiting the sun. I don't know why they didn't fall into the sun, but that's what they claim, all the way to Pluto, right? All these 8, 9 planets, depending on what version of Pluto you accept, whether it's a planet or whatever. But all these 9 planets, they say, were clouds of dust and gas that condensed locally also through a nebular hypothesis.
So the nebular hypothesis pertains to the creation of solar bodies, of celestial bodies.
Essentially the planets.
So they're saying you're saying it couldn't have been all this dust that turned into little balls here and there.
Right. Because, for example, take a little tiny object like Ceres, which is the biggest asteroid we got out there, and it's round, completely round, but it's a little marble compared to the Earth or the Moon or whatever. It's a tiny object. It's round. It's a round object, and Mimas, which is one of the moons out there, is even smaller, and it's perfectly round or quite round. And you say, how did that little guy, condense into this little marble? Because the sun, we can all understand. We say, well, all that mass, all that gravity, sure. But how do you explain the little marble?
Well, but by the nature of gravity, wouldn't all of them be round? Because they all essentially, it'd be weird if it was a cube.
Okay, first, you could say that, but then you got a different second problem that you got to add to that, which is differentiation. Means that there's all these celestial objects are layered. There's different layers of it. Like the Earth has all these different layers. The heavier ones in general are towards the center. The lighter ones are towards the periphery.
Like an onion.
Yeah, and in fact, we have gases like oxygen and nitrogen. We breathe it. Why? Because it's on the periphery. Hopefully it's not the other way around, have the gases on the inside of the Earth and the iron, we'd be breathing iron on the outside. No, it's the other way around. It's the lighter ones on the outside. What is that? You're looking at a star. That's the Earth used to be a star because that's why it's layered, and that's why it's also round. You cannot produce that kind of roundness unless you have this gravitational collapse that happened in the same way it happened to the sun. In other words, it was a nebular hypothesis gazillions of years ago, not 14 billion like relativity says. We're talking about trillions of years. And our Earth was a star that turned into what is known as a black dwarf. Okay, black dwarfs are stars that have already exploded, and they reached the end of their lives and turned into this solid thing called the Earth. Beautiful Earth, blue Earth with air and all that good stuff around it.
Did you ever get into why some turn into gaseous planets like Neptune or whatever, and some turn into rocky ones?
Well, I think in the case of Jupiter and Saturn, Neptune and Uranus, they did not have enough mass to ignite. So they are stars that came in, tried to come into being, but never made it. But an important point there is that if you look at the satellites that go around Jupiter, that go around Saturn, they're rocky planets. And you say, we got a problem, because if the nebular hypothesis for planets is correct, why did these guys end up with, Jupiter's just a gas ball, okay? But it's surrounded by little tiny moons that are all solid. And so how do you explain that? Because they should all, if they were all at the same radius from the Earth, from the sun, they should all be gas balls or whatever, or they should all be rocky planets. And now we have Jupiter, which is a gas ball, and it's surrounded by little rocky moons, satellites.
Oh, I like that question. How do you get a new star?
You get a new star by the rotation of gases. Again, the sun.
Well, let me give you
this. The nebular hypothesis is okay for the sun. I have no problem with the nebular hypothesis for the sun, and even for the Earth, billions of years ago. But the Earth was a captured dwarf star or a little planet. It was already a planet, and the last guy to appear in the solar system was the sun, that simply got all these existing planets and began to twirl them around.
Well, let's put it this way. If the sun were to explode and finish its cycle, so we have now the solar system without a sun, would there ever be another sun in that solar system again? Would there be another ignition and another star in our solar system?
Well, you got to look at the region of space.
Yeah.
Because, in other words, you got to look at let's look at the distances from other star system in the region.
Yeah.
That region, if it explodes, like if the sun explodes, it's going to leave behind an iron ball.
Yeah.
And who knows what happens to the Earth, the Jupiter, all that gets washed away to some other part of the, maybe all the way to to Alpha Centauri for all we know.
They take a vacation.
Yeah, they go out of the solar system. And what it would leave behind would be a an iron ball, which is what the sun would be left at the end of its life, and someday that would be captured by some other star as it drifts through space, and at some point it becomes maybe a planet, a black dwarf of some other solar system. That's the life that the sun can expect to have in its late.
He's an old man.
Yeah. Okay, let's continue here. We'll then later look at the questions and answer them. Let's just finish up here. Anyways, dark energy, it's the energy necessary to push all the galaxies away from each other, okay, which is what they're saying happened after the Big Bang. All the galaxies were formed eventually. First matter, then condensed into planets and stars, and eventually into galaxies, and then all these galaxies, everything is running away from each other. And you say, well, why doesn't gravity pull all this stuff back together? And so for that, they had to invent this invisible spirit called dark energy, which is pushing all this out. That's the driver of the expansion of the universe. That's what they're saying. Okay?
Pushing it out from the center?
Yeah, from a Big Bang, from, ground zero.
It's still exploding or what?
Yeah, it's still exploding. But they say it's not an explosion, but it is. It's a hand grenade. Yeah, I don't know. They keep saying they contradict themselves. They say there was a big bang, which sounds about right, like
Very
a
bangy,
hand grenade.
yeah.
But then they say, well, it wasn't a hand grenade. It wasn't a big bang.
It's just
You know,
a slow push.
and that's because they can't explain what happened on frame number 1 of that film. They always start at frame number 2.
Yeah.
Okay, that's part of the problem. Okay, we also covered a few people with mathematical physics honor roll. Okay, and we went through Brian Greene, Michio Kaku, Tyson, Nye, Carl Sagan. Just touched upon some of these guys, Paul Davies. Jim Al-Khalili, I put him separately because we covered quite a bit of his material, partly because he's backed by the BBC, and they made a long series of videos with him. He's also written a couple books, so I treated him a little specially compared to the others. He did a little more work pushing mathematical physics than some of these others. Okay, atheism, we covered that a couple times. It's the religion of mathematics. Why? Because atheism has to do with belief.
We're still doing philosophy, or not even philosophy. We're doing religion still.
It's religion. It's not philosophy. Philosophy would be, explaining a purpose, a reason. That's not what atheism does. Atheism says, look, I don't believe in God. Oh, you don't believe in God? Okay, you don't believe in the existence of God, And again, it's belief in existence. Existence, they never defined it. And then you can't use the word belief with the word exist. Okay, you don't believe that this chair exists. The chair exists whether you believe or not.
Well, you could talk about belief of existence, couldn't you?
Could you give me an example?
Like, I believe
You believe.
there's a washing machine over there, but I can't see it. It's just a belief thing.
Yeah, but you haven't explained the purpose.
No.
Or see, the issue is that science is about explaining. You got to have that word explain in there, otherwise, what's the purpose of science?
But if there's an explanation, there's a question.
Huh?
You can't explain something without a question. What's the question that you're explaining, or what's the?
Well, yeah, I mean, that's the context. In other words, you have to explain a purpose for something. Mm-hmm. And one of the issues there, an important issue, is people say, well, why is there something rather than nothing? When you ask that question, you're already implying God, because you're implying that God or an intelligence or whatever out there already had a purpose, a reason for creating the universe. So whenever you ask, why is there something rather than nothing, it's an irrational question, because you're putting in a physical context.
It's a loaded question.
You're putting in a physical context, in the context of physics, you're putting a question of philosophy, or they're mixed. You're trying to say, well, why is there matter?
The problem with
but you're saying there was a purpose for someone to create matter. That's what you're saying. That's why it's an irrational question.
There's a I don't want to say wrong assumption, but yeah, there's a wrong assumption that goes with the question. Uh-huh. When you ask why is there something instead of nothing, it's like you're already implying that there was a purpose for there being something.
Right. Right, and what is purpose means God. You're already implying God when you say that question. People don't even realize that. But you're implying an intelligence, which is what we usually identify with God. Some intelligence, a watchmaker out there that said, I'm going to create a watch. Well, why are you creating a watch, God? And I'm creating a watch because, and what comes after that is irrelevant, because you already answer the question that there is a God, and you must believe in him because he had a purpose for us, or for the world, or for the universe. Okay, finishing up here. Let's continue. Touched upon some of the rising stars. These are the new generation of people. Some of them, I just went and got probably some of the most noticeable people on the internet. I missed a couple there. Dr. Dave was one of the guys that I missed there, but I covered him one day as well. And lately I've been doing the Nobels, why people won Nobel Prizes. We need to know what all these people invented or discovered, what they did for humanity, because that's what the supposedly Nobel created a prize for, those who helped humanity the most in the last year or whatever. And finally, obviously, again, the issue of extinction.
It always comes back.
Yeah, we always have that extinction issue. It never leaves us, because I suspect that we're not going to make it past the 21st century. And because I don't think the economy of man's artificial economy, can grow forever. And part of that is that we can't reproduce forever. The curve of the reproduction curve since 1963 has gone, has tapered off. It's become asymptotic. It approaches the asymptote. And when we reach that zenith, that maximum point, that's called zero population growth. We do not increase any further than that, meaning that now we have a problem with what? With demand, because demand is a function of population. Ultimately, it's a function of population. And so you don't have an increasing population demanding more products. The companies don't sell, so they have to lay off. And when you lay off, those people have to make a living somehow. And what happens is usually they cling to the government, more and more and more of them, until finally the whole system collapses. So that's one of the issues that's going in the background. There are more issues involved with the extinction, with the economics of man. But the point is that I'm saying that economics is going to crash. Because it crashes, meaning that money is no more, trade is no more. You don't trade because there's nothing to trade. The medium of exchange, the currency that we use, is no more. So now you have no way of making a profit. So there's no reason for you to go out there and sell vacuum cleaners or whatever, because whatever they give you, you can't use anyway. So what are they going to give you? Paper for a vacuum cleaner or whatever you're selling? So trade is no more, and because of that, the whole system collapses. And if the whole system collapses, maybe there's no big deal. The big deal is that the people who produce food now have no reason to produce it or distribute it to the cities. And that's when we have a problem. Because the only reason we stay alive, the only reason we live one more day is because we eat. It's food, besides breathing and drinking, right? But food. Everything else is expendable. Even sex, not for me, but for other people, is expendable. You don't need computers, you don't need cars, you don't need airplanes, you don't need houses, you don't need any of that. What you do absolutely need is food to live one more day. Okay? And if right now we're producing the food ourselves, and we produce it for what? For money, for gain, for pecuniary reasons. Once that's over, no one produces food for the rest of us. And people say, well, I'll produce my own food. Well, that's if
have you
your
tried?
neighbor. Well, that's one issue. But the other issue, city boys,
that's hard.
City boys have a problem producing food. But that's one issue. That's probably an issue you may be able to solve. What you won't be able to solve is defense. Right now, defense consists of the legal system, military, police, all these things. They vanish. There is no government. And so there's no one to protect you. Okay, and you say, well, a new mafia will arise. Al Capone and his boys, they take over some group, some gang. No, because food is the only thing that's going to be important. And a gang cannot stay together unless they have food. And they can go in there and rob, but then, they're going to fight amongst themselves as well. There's no way, there's absolutely no way that anyone will form an army. Not anymore. Armies were okay in the old days when we created them, because there was an extensive farming that maintained that army.
Everyone was into farming.
Right, everybody was into farming, and so some people donated people to the army. They donated their sons and not daughters, but sons. They became soldiers. But there was a foundation, an enormous foundation of farming that maintained those armies. That won't be the case. So right now we have very few people producing food for everybody in the world. So it's the other way around. Now it's not an extensive population producing food. Now it's a very, very tiny population. 1%, around 1% in advanced nations, developed nations, maintains the rest. And so we have a problem. We have a problem because once that collapses, then there's no reason to produce food or distribute it to the cities, because there's no more reasons for it to exist anymore. The distribution system, our economic system. Okay, and what else? Okay, well that's essentially it. So let me go into the questions and comments, and we had some from last week, so let me go with those first, and then we'll go through the list of people who are here today. We'll try to answer those as well. Okay, we start out with what? We start out with this, which is what I put the other day, which is mass. Okay, we have the same astronaut at two locations with respect to the Earth. We weigh them at a higher altitude and a lower altitude. I already gave one of the answers to one of those questions. They do have a different weight, okay? And the one on the bottom weighs more than the guy on the top. And the question you got to answer is why? What causes the one on the bottom to weigh more than the one on the top?
I mean, it's common knowledge that people in higher, the objects in higher, like in a mountain, weigh less. If I were on a mountain, I would weigh less than if I were on ground.
Yeah, and we know this from the notion of field. What is a field? It's a value at each point around an object, whether it's electrical, magnetic, or gravitational. It's a set of values around an object. It's a radial phenomenon. As you go farther and farther away, in all those cases, the strength is weaker. The question is why? We need to answer why. What's the physical cause? And, okay, so we don't have an answer, but some people gave mass and gravity a shot. And here's one fellow, and he says the following. He says, if I can read this thing, says, weight is a measure. We use it to calculate things such as density. Mass is derived from the periodic table of elements. Well, great, but I need to know what mass is. We need an answer. We need a definition for the word mass, and we don't have one there. Okay.
Well, we need a physical interpretation because we need to explain what is the mechanism that's making the lower astronaut heavier than the higher astronaut, right, even though they're the same exact astronaut.
Yeah. And it would help if we start by defining mass. And right now, nobody can tell me the difference between mass and weight. Everybody goes to high school, or that goes to high school, learns that mass is the quantity of matter. And we had already Mr. Wheeler and Mr. Taylor. They wrote a book. These guys are head honchos. Wheeler died already, but a couple years ago. But they said mass is not the quantity of matter. Okay, and I explained the other day that if you accelerate a particle, which is what they do in those accelerators, or what they think they're doing, they say it gains more mass. So obviously it's not the quantity of matter, because then you would say, what, did the particle increase the amount of matter as it went by, or are we talking about how much it presses down on the scale, which is weight? So again, there is no difference between mass and weight, because everything we've done on Earth for the last 500 years, we've always used weight. We never counted atoms. We never counted quantity of matter. Okay, we just assume that weight is a measure of the quantity of matter. Yeah. Okay, that's all we have. And if you accelerate the elephant, he weighs more on the scale. No kidding. And it's not the same thing for the elephant to stand on the scale than to drop him on the scale. Yeah. And so that's what they do with mass. Okay, and the fellow continues, says, if trying to ask what is mass made of, I'm going to go with Nikola Tesla, Walter Russell, Nassim Haramein, Eric Dollar, David LaPointe. And he says, how many morons in one sentence? Yeah, there we agree. How many morons in one sentence? Now, you got to define what mass is, and if mass is a concept, then you cannot ask, what is mass made of? Love is not made of anything. All concepts are not made of anything. Intelligence is not made of anything. Data is not made of anything. So you can't say that mass is made of something. So that is not the question. The question is, please define the word mass and show how it is different than weight. And show me an example, because we don't have an example. What we do is use analogies and say, for example, that if we take the grand kilo in France, which was the standard of the kilo until the year 2019.
Until it lost a few atoms.
and you take that to the North Pole, it's going to weigh differently.
True. Yeah.
And you say, well, the weight changed, but not its mass. Well, it did, because the way we determine its mass is by weighing. So, yeah, mass changed also.
I mean, it'd be kind of hard if we counted atoms.
Yeah, right. They can't.
It'd take a long time.
And like Wheeler says, you can't count atoms, because which atom are you going to count? The uranium atom, the hydrogen atom? Uranium has 92 protons. It's like 92 hydrogen atoms, more or less, okay? Not to mention the neutrons it has. Okay, so yeah, you can't do it. So yeah, you got to define what mass is, and no, it's not what mass is made of, because concepts are not made of anything. Okay. Okay, let's get back in here. One fellow says, he says, I'm not mocking you in any way. Oh, go ahead. I have no problem with people mocking me. I mean, I've received mockings and mocking birds for the last 20 years. So join the crowd. Don't worry about offending me. Your job is to offend me, okay? And I don't take offense very easily.
Among other things. That's not the only job.
Yeah, so, no, you can cuss my mother on my channel. As long as YouTube allows it, I don't care. I mean, I don't care. Really, you don't. Now, he might care. I know. I don't know.
I do it too. I don't care.
Okay, another. Since your cosmos is finite. Absolutely not. I don't know where you got that. Cosmos equal universe equals matter and space, meaning it's a concept. And concepts are neither finite nor infinite, okay? My love is infinite, but, it's...
I guess he means the matter in the space?
Yeah, he probably did. Yeah, so I wonder how the tension between all the ropes in the cosmos remains maintained. Well, I'm just going to give you two answers here. One is that the velocity of light is a constant under the rope model. Why? Because it's the inverse relation between frequency and wavelength, link length, okay? So C equals frequency times wavelength is the equation of a rope. Okay? And you have it here, the more we torque this, the more links you have, and the shorter each link. Frequency, wavelength. We got it. Now you untorque it, you get fewer links, each link is longer. Frequency times wavelength. We got it. Okay, so the velocity of light is a function of those two. That is the equation of a rope. There's no other entity we can imagine that can mimic or simulate that equation.
What do you mean by tension is not a force?
Okay, so then if the velocity of light is the same between any two atoms, because the rope only changes frequency for wavelength and vice versa, then what happens? If the velocity of light is a constant, that is the tension in the universe. And so the question here is, let's go with the third one. He says, tension should have done its work and pulled all the masses, meaning, like Newton said, why doesn't all this lump into one place? And Newton had a good answer for that, and it was the notion of galaxy. And that's that, you have all these galaxies out there, and they're all doing their own thing. That's one issue. They're all like centers of gravity.
They're too far apart from each other to...
First, they're too far apart, but then you have all these are rotating and moving in different directions, and this is what creates the universal tension on the rope. We don't even know if all the matter that is in existence rotates as a whole or in different directions. So that maintains the tension on the rope.
But
and
centrifugal force?
It's centrifugal in a sense. I think it's just rotation in different directions that maintains the tension on the rope. And one of the issues there is maybe we have tension here, but maybe on the other side of the universe, there's a little slag coming in and then it goes out. I think there's all these motions going on, and that maintains the tension on the rope.
I mean, I imagine it like a bubble of water. Like if you had a bubble of water in space, it's just kind of moving, doing its own thing, where the edges of it are going in and out, like constant motion.
The edges of the bubble, you mean?
Yeah.
Yeah.
That's how I imagine the edges of the matter in the universe.
Yeah, I think.
Not the space.
I think first the fact that we have all these islands known as galaxies. That's one issue, and the other one is that the whole universe, in other words, the matter of the universe, is rotating in different directions. And maybe one is going out while the other one's coming in. I think you have all these motions, and that keeps the tension on the rope, I think, all around. It's the motion of the galaxies that maintain the perpetual motion that we have of matter. Okay? And so he says, tension should have done its work and pulled all the masses. Well, the problem is the word tension. Tension does not pull. Tension and pull do not go together, except in mathematical physics. They think tension is a force. Tension is not a force because no one wins the tug of war. Force is the opposite. Force, someone wins the tug of war. Whether pushing or pulling, there is a motion in one direction or the other. Tension, no motion. Okay, it's think of tension. I always like to think of tension as a stick made of a single piece. You know, it doesn't shrink and doesn't get longer because it's made out of a single piece. That's tension. Essentially, it's a way of visualizing tension. Just a stick made of a single piece. Hey, you're back. Okay, another issue. We had a problem with squares. Apparently, people have problems with squares. Okay, let's find out. If I can get this
Squares?
Yeah.
You got a problem with squares?
Yeah, because people will say a square is not an object. And I'm saying, yeah, it is. See, it's got shape, and that's the definition of an object.
Your definition.
Okay, then people have the option to redefine it and defend their definition. If you don't like the definition, that which has shape, your job is to define it. People never define it. They just want to argue that, no, a square is not an object. No, that's in ordinary speech.
We're getting backed up by a lot of questions here.
Yeah, I know. We'll get to them.
We're going to be here all night.
He says, define mathematically perfect. Okay, if it's defined, it's not an object. Let's see what he defined. He says, square, 4 perpendicular lines that end at the next. Okay, so I put these 4 lines, 2-dimensional lines, okay, because there is no object that's 0-dimensional or 1-dimensional, right? So we had 4 squares there, or 4 elongated rectangles, okay, and that's not a square. What that or a physical object? That's 4 different physical objects. That's a concept. Okay, so no, if you can define it, it's a concept, and a square is not what you see there. Square is what I showed there in red, which is a single piece, okay, and it's got shape because it's got some contour of some kind. So, a square is an object by definition, pursuant to the definition. You don't like the definition? No problem. Give me your definition and be prepared to defend it with sword and shield because I'm going to attack you. Okay, another issue. Fellow says, explain so a blind man without eyes can understand what you're talking about. Okay, Helen Keller, she was blind. She was deaf also, or more or less deaf, I think, and mute. She could not speak. And Anne Sullivan made miracles out of her. And she did it by touch. She learned a lot by touching with her fingers. Okay, she
you not only have to. You got to work with what you got.
Yeah. So fortunately, she was not quadriplegic as well. But the issue is that it's an irrelevant issue. You have to define what an object is.
What are you talking about?
Well, because he says, how do you explain a square? The issue was
explain a square.
Yeah, okay, or how do you explain it to a blind man because he's never seen a square? I don't care if the blind man or the dead man understand me. When I die, a square remains a square. It remains with shape. By definition, it's an object. So you gotta define the word object. You can't just keep talking around the subject. You gotta define the word object. You gotta know what an object is, especially for the purposes of physics. Why? Because the golden rule says, the golden principle, you can't do physics without an object. What would there be to study if we had no objects? What would there be to analyze? What would be moving? What phenomenon would be happening?
I guess the problem that happens if you don't define object is you end up with weird theories of things popping in and out of voids that aren't there.
You mean like from the vacuum?
Yeah, you start inventing things that things don't do.
Yeah. And you start moving concepts around. You call them objects, but they're not objects. What they are, you call them particles. And you say, well, are you talking about a little speck of dust? Oh, no, it's a number. It's an amount. Oh,
it's a number, then we're not talking about shape.
Right. So, yeah, they never defined the word object, and they skipped that, and that was an important step. Okay, another question, comment here. Again,
we're
with
still on squares.
Oh, yeah, a lot of people with squares.
Oh, man, we're stuck on squares. We're in for the long haul. Jesus.
A square is a 2-dimensional representation. Well, I don't know what a representation is. All I can tell you is only objects have dimensions. So if it's 2-dimensional, whatever 2-dimensional is, it's not a representation, it's an object.
I guess people have the problem that defining a square as an object because people always think of objects as that which you can see or touch.
Right.
A thing that they're talking about existence. They're talking about location.
Exactly. That's the problem. And that's the notion of ordinary speech. We say the table is an object because you can see and touch it.
You're saying there are objects that don't exist.
Not first, that don't exist. Second, that we can imagine. I can imagine a table. That one doesn't exist. Geometry, the two-dimensional plane geometry at least, it's just imaginary. And that means you can visualize, you can draw it. There's a shape there, but it doesn't exist. What exists is the pen and the paper and the ink or the chalk or whatever.
Maybe imagination is what kind of messed it all up, because if we didn't have imagination, then there would only be things that are.
And that's where people get confused. They think that because it's imaginary, it's a concept. No, if it has shape, it's an object, even if it's an imaginary shape.
Is there a reason to keep that definition so rigid?
Yeah, it is, because it's the malleability of that definition, the fact that we've made it anything that's imaginary, we say, well, that's a concept. No, that's in ordinary speech. In physics, you cannot have that definition, partly because, usually see, touch, which is what we usually identify with objects, that definition requires a second object. Only another object can do the seeing and the touching. You need two objects to define one.
We need a referee.
And it's an irrational. Besides that, it's also an opinion. In many cases, did the asteroid really touch the moon?
We're gonna go through all of these.
We're almost there. Okay, let's keep going here. Otherwise, we'll spend the whole night here.
Hey, we're on the cubes.
we move on to cubes. Okay, so here goes. Cube, the only shapes we consider as objects, dictionary definition of object, are third dimensional. Cube is a third dimensional representation, again, representation, right, of a fourth dimensional hypercube, a tesseract, in all other higher dimensions. Well, there are no higher dimensions.
Higher?
Yeah, except when you drink too much, then you have higher dimensions. I know, I've been there once. But no higher dimension. But let's look at the tesseract real quick, which we need to look at that because people think a tesseract or a hypercube is a physical object. Supposedly it is, but it ain't. Because they define it as a four-dimensional object. No, it's a three-dimensional object, actually, moving through time. That's what I want to show here. The first issue here is that, the dictionary definition requires a second object, which is see, touch. So again, until you define the word object, you have no case. You need to define the word object. You can't say, well, this is what we call object normally. We don't care what it's normally. We're saying what it is for the purposes of physics, for the purposes of science, and it has to be a scientific definition, which means one that you can use consistently. You cannot use the see-touch criterion or criteria in a consistent way because it requires a second object, among other reasons. And a lot of it is opinion. But here, let me show you something. Here's a tesseract, and you can see it's moving around. Okay? And you say, okay, I understand that. It's a three-dimensional object that's moving in space or rotating or whatever.
It's like Jell-O.
Yeah, but see, let me tell you the problem there. The problem there is that the inside cube, the nested cube, the one that's on the inside, is growing and becomes the one on the outside. That's what a hypercube is. A small cube that's becoming bigger in all directions. Okay, so what you see there, those corners, that's the axis of time, a number line. And the problem here is that they're moving time, they're moving motion itself. What? That's what it is. So here, let me show you piece by piece what they're doing. They're saying that a cube that grows over time is a tesseract. That's what it is. You have this movie that turns into a photograph.
What?
You have a little cube that goes bigger, bigger, and bigger, because that's what it is. The inside cube is growing in all directions, becoming the tesseract.
They're saying the object, the picture that we're going to show you is the process of a cube getting bigger.
Because it's through time. Yeah. The fourth dimension, according to them, is time.
You can't have a picture with time.
Right. And what they're doing then is rotating time.
What?
Because, see, what they're rotating here is the entire hypercube. See? So what they're doing here is rotating time. You see there? See what's happening there? They're rotating time itself. They're rotating motion because the little cube is becoming bigger at the same time that the whole thing is rotating through space. And they're saying, oh, the tesseract, the four-dimensional tesseract is rotating. No, that's irrational because you're rotating time.
I mean, wouldn't all objects be four-dimensional according to? I mean, if you made time a dimension,
Yeah.
aren't all objects four-dimensional? Why do they
Yeah,
go to
that's
the
what I'm
tesseract?
saying.
Why do they need the tesseract?
We don't
to be
need
this
it.
Four-dimensional?
I'm four-dimensional
Yeah.
too because I'm three-dimensional moving through time. I'm a four-dimensional object. Everything in the universe is four-dimensional according to them because they're talking about an object moving through time, or as they say it. What it is you have an object in motion, and the worst part is when you move. When you have that movie and you rotate the entire movie, including time and motion.
That's what I understand.
That's what a tesseract is. It's a rotating time. That's what they're doing. So yeah, it's totally irrational. Mathematically, you can treat it any way you want because it's mathematics
numbers.
is all abstract. You can do whatever you want there. You just put a variable and say x equals that. You move x, no problem. But you can't turn that into physics. And that's why these people cannot imagine, say, well, the fourth dimension is unimaginable. No kidding. Yeah, everything is three-dimensional out there, okay, that exists. That's part of the notion of existence, If it has location, it has to be three-dimensional. If we didn't have the background of the visible light spectrum, we wouldn't know what light was, would we? Well, again, you got to define the word object. We got to know what that what is. That word what is an object. And know and knowledge, that's religion. Knowing has no place in the definition of object. There's no provision for knowledge in objects or existence for that matter. Neither one. Okay?
It's done only with assumptions.
It's done with definitions. You define, and then existence, you define it. And then if you say the table exists, well, let's look at the definition. What does the word exist mean? It means a physical object that has location. That's what you just said. That's what you meant when you said the table exists or the chair exists. And the one that doesn't exist, maybe the one I'm imagining, that one doesn't exist. Why? Because it's an object, but it lacks location. And if it lacks location, it doesn't exist by definition, not because I believe or know. So knowledge plays no part in all this, okay? Especially in the word exist or the word object. No provision for knowledge or for belief in the word exist. Okay, last couple ones here. On Superman, we had a couple issues there. One guy says, is a drawing an object? I mean, if you remove the paper and ink, there isn't a Superman left behind. But I can visualize Superman in my head as an object.
There's that imagination messing things up.
Okay, the only comment I want to say on that, I mentioned this in the past, but let's just show this, okay? A circle is not a drawing, okay? Or a partial drawing, like, half a circle. Circle, what you see on the right, a finished product. That's a circle, okay? Not the one that I'm drawing. So drawing Superman, just want to make sure that if I don't finish Superman or the statue of Superman, well, that's not Superman until I finish it. Okay, it's got to be a finished product. Then I can say that's Superman. If he's missing his legs, well, that's a different kind of Superman. Circle is a finished product. You have to finish it. Okay, so drawing is a verb. Okay, and just let's keep that in mind. Drawing. The motion of drawing something is not the object. So when I say, sometimes I say that an object is that which you can draw or that you can point to, okay? Those are just to get you into the habit of thinking that we're talking about shapes, okay? But the drawing is not the object.
The process is
the process of drawing is not, or sculpting or whatever is not the object. And last question here, again, Superman. And what is it? We have this. Fellow says, none of the imaginary phantoms you come up with, Superman halos are not objects. Well, you got to define what an object is. You can't say it's not. You got to say what it is.
Well, again, they're talking about objects in the sense of existence.
Yeah, but he's got to define. I need a definition.
Yeah.
I'm sorry. I need a definition.
I'm just talking about the notion that everyone comes at object with is things that are in reality.
That's one issue. But the other one is they skirt the issue because they don't want to define the word because they can't define it.
Yeah.
Or they go with the definition in the dictionary by default, which is an irrational definition that we cannot use in physics. And that's why they don't define it, because as soon as they define it, it's easy to tear apart. Especially because it usually involves two objects. See, touch involves two objects, and that has to do with existence and not with object. And people never realize that. David Hume, Immanuel Kant, they both had that problem. They couldn't distinguish between existence and object. Okay. And last issue there, if so, I came up with a 3D box drawn on a paper and can draw a fly on it. Tell me which side it is on. Irrelevant. There you have a fly on a box. Okay? And, okay, so what's the issue? I mean, we need to define the word object. Just define the word object, and then whatever follows from that definition. And while you're at it, define the word exist, okay? Okay, let's open the floor up for questions. What questions do we have, sir?
Crap ton of questions here.
Let's see. Whoa, okay, let's start at the beginning here.
Let's go here. How do ropes create pull or tension, though?
How do they create? Well, they don't create. That's like saying God created motion, or God created the universe, or God created matter. You don't create. Motion is already there. Motion, you can't say that motion started, because that's irrational. That would require an outside force of some kind to get the ball rolling.
Yeah, but when you're earlier,
the same for object, by the way. You know, you can't imagine how matter came into being, and you cannot imagine how motion started or came into being.
Okay, but earlier you said that tension was like a stick.
Yeah.
So, assuming you had 3 atoms, each attached with a stick,
yeah.
How is there gravity?
Huh? Gravity?
How is there pull?
Oh, I see. Well, again, you have 2 against 1. I got that
unfair.
Huh?
It's an unfair fight, 2 versus 1.
In a way, I've got that in the book because I've got a good example of that, of how if you have only 2 objects in the universe, 2 atoms, and you can't create gravity. The only way you can create gravity is by aggregation. Remember, gravity is not a pull it's not pull. What it is aggregation. You have more over here and fewer over here. Okay, and so you have fewer atoms here, many atoms over here, and what happens is one object drifts towards another, and as it comes closer, the ropes fan out. Okay, so yeah, you need, if you have 3 atoms, then you can produce gravity, but you cannot produce gravity, for example, with 2 objects. They can rotate. Let's assume you could rotate them. Remember, Mach's principle requires the stars to pull on you. But let's get rid of all the stars, all the matter.
Rotate with respect to what?
Yeah, right. You wouldn't have. But let's assume you only had 2 atoms tied by a rope, and that's the only thing swinging around in the universe. And let's assume it just swings around. Okay, one atom with respect to another. Let's try to visualize that for a second. Well, at that moment, all you have is tension. There is no gravity. Gravity is a force, but only in the sense that as an object approaches another, the ropes fan out. And it's the fanning out of the ropes, the fact that you have more and more what we call effective ropes operating between those 2 objects, that creates that notion we call gravity, that pull force that we see in our macro world.
What happens to the thread, rope, slack as objects approach each other?
It's eaten up. In other words, remember, the atom is made out of the same thread as the rope. One thread goes through the center of the atom, the other one goes around. And as one atom approaches another atom, what happens, the rope, it gets reeled in and out the other end. It's like sliding a bead on the abacus. The bead does not eat up. It reels in, so to speak, the wire on the abacus, and in that sense, the best analogy maybe I can give you.
Through.
It just slides through. One thread goes over, which is the one forming the electron shell. The other one, the one that goes through the center, which forms the proton star, it just slides through those two threads, and they just go out the other end. So it always maintains tension because remember the atom is also pumping and vibrating. There are different motions. One of them is the Mossbauer effect, which is when the atom is stuck to a crystal lattice, it doesn't recoil. So there's different kinds of motions. And so you got to look at all these motions together as an atom moves, vibration, expanding and contracting, doing its quantum jump. And while doing that, there's no reason for the rope to slack between them because the rope is being pulled by every atom in the universe.
There's too much motion for there to be slack.
And the atom, the rope itself is always under tension. The only thing that changes is frequency for wavelength. In other words, the number of links and the link length. That's all that changes. C equals frequency times wavelength. That equation is the equation of a rope, and it's always a constant. That is a measure of the tension on the rope everywhere in the universe.
Saying love does not exist, as in has no shape and location, is fine, but I really don't like having no counter statement to it. If love doesn't exist, if concepts don't exist, what do they? Like love, justice, they don't exist because they have no location.
Yeah.
What do we say to concepts?
Oh,
they don't
what word? Yeah, remember, in ordinary speech, we say love exists, intelligence exists, data exists. We say that. That's in ordinary speech because we don't have to be careful with our language. In physics, especially science, but the branch of physics, you have to define these terms because physics is not only the science of objects, but it's the science of existence. So you can't say, oh, I'm going to use the same definitions as I have in ordinary speech. You cannot bring that definition, that loose definition, saying, oh, love exists. You can't bring that into physics. You can't, because then what do you mean? Now you got to define the word exists, okay? And same with God. If you're going to say God exists or God doesn't exist, well, what do you mean by that? What do you mean by God exists? What do you mean by God doesn't exist? And that's where you got to bring in a definition that you can use consistently. And what I'm saying is, first, you need to have an object. That rules out all concepts. So you cannot say that love or intelligence exists in physics. Okay? In physics, in science, in a way that you can use consistently, rationally, okay? Scientifically.
I mean, I guess we're talking about like a pattern. You don't really say a pattern exists, but what do we say instead?
Well, you can't use the word exist with concepts in physics. In ordinary speech, you can use it. You can say,
but in science, if we're talking about philosophy, for example,
but
philosophy
remember,
is under science, so we do have to define. We're talking about concepts. We could be talking about concepts under philosophy. So, you can't really say.
But that's the branch of philosophy.
Like when you say we've noticed a pattern or we've discovered a pattern in the natural world, for example, whatever it might be.
Yeah, but when you say pattern, you're talking about a behavior.
Yeah.
And we use the word pattern. Pattern is very misleading because, when I use the cookie cutter, I left a pattern on the dough. Mm-hmm. And so people relate that. Those are the words that fall on both sides, and they say, "Oh, pattern." I like that word because it unites philosophy with physics. On the one hand, I mean pattern, like a pattern of behavior, and on the other, I'm saying pattern like the
same thing over and over,
the cookie cutter or whatever. No, we can't use words that are ambiguous. You can't use the word exist in the context of concepts in physics. In philosophy, again, you don't need it. You don't need the word exist. What are you going to say as far as like if you're trying to explain something in philosophy? Why would you say that love exists in philosophy? You're trying to explain.
You're explaining the phenomenon of a behavior.
But then you would not need to say at no point. You would not need to say first that a heart represents love, and second, you do not need to say that love exists. You do not need to say that. Not in philosophy, which is a branch of science. So concepts, no, they don't exist. You can't use the word exist with concepts.
Does Bill's rope hypothesis explain how complex orbital shapes within atoms are formed? Hydrogen atom orbital seems easy enough. It's just two balls. But how can some atoms have different shaped bubbles within bubbles? Like, I don't know, uranium atom. It's just bubbles on bubbles on bubbles.
Well, remember, the simplest way, you got to go slowly because you got to visualize the simplest and then work your way to the complex. You have two hydrogen atoms. When they come together, they form the H2 molecule, gas molecule. Why did they do that? Because the rope between them, remember, it goes over, one thread goes over the top and the other one goes through the center, and the atom slides through those two ropes until it meets the other atom. That means the rope disintegrated completely, in other words, disappeared. What happens when these two atoms touch? Electron shell against electron shell, or membrane against membrane. Well, they start screwing into each other. If they're both rotating in the same direction, meaning from one end you can see both of them going clockwise, meaning from one end you see clockwise, if you go from the other end you see it counterclockwise, right? So if the electron shells are spinning from one point of view in the same direction, they screw into each other and they form the H2 molecule. If they're both spinning in opposite directions, they bounce against each other, flatten out a little bit, and then they bounce away. They have no chance of merging and forming the H2 molecule. So what happens, the threads get coupled one into another and form that figure 8, which eventually is a single oval. And that's just for the H2 molecule. You can see how that can be extrapolated to other molecules. It's even very hard to draw. Okay, but I've got like iron. Iron has 2s, 3p shape. In other words, it's got these p orbitals, and what they are is essentially what we've done there is blended several hydrogen atoms together to form what we call iron. How was that done? It was done in the sun through pressure, in a star, right? Through pressure. But yeah, what happens is the threads have no problem in merging one into the other. They blend because they're all made out of the same threads. It's a single thread in the universe. So it's like, it meets each other. One membrane meets the another membrane.
Okay. Can you talk about touch? Is there a scientific definition for the word touch?
The definition is zero distance. Zero distance. But the problem with that definition is that zero distance means the two objects have become one. So we have your finger touched the table. In ordinary speech we say, oh, my finger touched the table. But in science we can't say that, because if it touches, means there's zero distance. There's no space between them.
You can't have the surfaces.
Yeah, there's no individual surfaces. The surfaces have become one. The finger has become part of the table, and so now you don't have two objects. You have a single object. So we have a problem with the word touch. The word touch, like the word exists, people don't pay attention to those things, but they're very important, because people say, well, it touched. My two fingers touched. Well, have they become one?
Do they have to become one for their services?
Well,
to
I mean, if they don't, well, hold it. This is the point. Here we have two fingers, right? We have two. We say the finger touched. Mm-hmm. In ordinary speech, no problem. We have no problem with it. The problem is when you try to do physics scientifically, okay? And you say, well, what do you mean by touch? Well, touch is zero distance, because if there's space between them, if I still have space, then they didn't touch.
Yeah.
But if they touch, we mean that there's zero distance. In other words, there's no space between these two fingers, meaning they became one object, and you need two objects to touch.
But
that's how we define touch.
But they became one object. It depends on where you cut off an object.
No.
In your mind, because when you're talking about an object, you're kind of giving it an imaginary shape. Like when you're talking about a chair.
I can solve it for you. Look, two fingers, right? Yeah. In physics, science, right? We say they touched, but they didn't touch because there's space between them, right? No. How do we? There's space. There's still because as much as I press, there's still individual.
The atoms are raising up on each other.
There's still space between them, because what you have is electron shell against electron shell. And if they don't blend, then they're two separate objects. There's still space between them. Tiny little space, but there's space between them. But this is the solution. Let me tell you what the solution is. The solution is the following. Two objects become one. That's called touch.
Two objects becoming one is touch.
Right. See, we have a different definition than we have in ordinary speech. In ordinary speech, you say, well, you touch because what? Two surfaces came in contact. No, that's not touch in physics because there's still space between them if they're two individual objects. The only way they can touch in physics is they become one object. And as long as you accept that, we have no problem.
We have a small debate over the word real.
Real.
That which can be thought of.
Again, that's ordinary speech.
No, this is a definition. An official definition. That which can be thought of. Can that be used for anything? Is that a legit definition?
No, it's not.
Depends on what you need it for, I guess.
Well, in ordinary speech, yeah.
No,
but in physics, you can't.
That which can be thought of. What's the problem with that? Like that which can be imagined.
You mean for the word exist. In other words, real meaning exist.
I guess.
Because real is a synonym of exist. So use the word exist. Don't use the word real because you get confused. You're saying if I think of something, it exists. Is that what fella's saying? I guess.
I mean, it depends on what explanation is being used for, I guess, because you can't really just have a definition in a vacuum. It's really definitions are always for a purpose. Right. You can't just kind of define the word, I don't know, love just for the sake of it. You kind of have to define it in context of a question you're trying to answer. Well, that's the question. Is there any point in defining the word object if you're not going to use it for anything?
Right. That's the first one. You can't. And the other issue is, again, if I imagine something, you say, well, it exists because I can imagine it. Well, we're creating existence every second then. Everybody imagines stuff. So we got 8 billion people creating existence. We're more powerful than God here. You're creating existence. I mean, what's the point of saying that anything that I can imagine exists? Because the definition of exist is anything I can imagine. Well, what can you use that for?
Yeah,
what's the purpose of that?
It depends on what the explanation is.
Yeah, it's a worthless definition.
I also have another question. If matter can't really be created or destroyed, does that mean that the universe keeps going on forever, doing similar things?
Exactly. There's no beginning to the universe, but that creates a serious problem in our minds. It just blows your mind away, and that's when you need a psychiatrist. Because what it means is there was never a first human being. Because before the earth, billions of years ago, there was another earth or similar earth, similar planet like the earth somewhere in the universe, and there were humans there in that planet. And billions of years before that, when there was another planet and there were humans there, human-like forms, intelligence that developed there. And before that, there were another planet billions of years before that. And you keep going and going and going and going because there was never an origin to the universe.
But he's also saying there's never going to be an end. There's no end to it all.
Not only is there no beginning or end, just like there's no beginning to matter and there's no beginning to motion.
It's trippy.
And it just blows your mind away because we're not used to that in ordinary everyday life. We always think that a baby is born, and we say, okay, that's the day he was born. That's when he started, and this is when he died. This is the beginning. This is the end. The Alpha and the Omega. We're used to that. So we're not used to things which are eternal. So when someone says, look, there was never a first human being. There was never a first planet. There was never a first galaxy. It's always been there. You say, well, what do you mean? How can that possibly be?
It's definitely trippy.
It blows your mind away. It does.
Is gravity tension or pull? I guess we covered that.
Yeah, gravity is tension at different locations.
But isn't it pull created by tension?
No, there's no. First of all, I want to make.
What's the difference between pull and tension? Let's start there.
Okay, pull, someone wins the tug of war. There is force equals mass times acceleration. Means that acceleration means you change location.
But that is gravity.
In tension, there is no change in location.
We're talking about gravity?
No. First, let's clarify tension versus force. Gravity is tension at different locations. If you stop the movie and you look at just one frame, no motion, no time, just one frame, just a snapshot, a picture, right? The whole universe is frozen at that point. what you see is the number of ropes. You count them and say, okay, there's a gazillion ropes. There's 1 billion ropes. Now you move the object closer to the Earth, for example, right? Now you look at that frame. You freeze the universe. You just look at that frame. Now it's got 1,000,000,001 rope.
Well, but
now you have one more rope.
But it's not more rope; it's more active ropes.
More effective ropes. Yeah, more effective.
Very important difference.
Yeah. So what we're saying is the same number of ropes, except that they're no longer on the same axis, and so you have tension, not force, but tension at different locations. Okay, and that creates the notion for us called the force of gravity, because what we see is the cup falling towards the floor. And what we don't understand, or what is difficult to visualize, is that what you really have is that cup at different locations, and what you have is different tensions, different number of effective ropes at different locations. More and more ropes, effective ropes, acting at different locations as it gets closer to the center of the Earth.
Is it safe to say there's more triangles, essentially?
Yeah, the angle changes. It changes the angles of the ropes as well. You know, there's two effects. One is the angle, and the fact that they're no longer on the same axis as they were before. And you can see this very easily when you have two objects very far apart. If you take 100 guys and you hold their ropes, every 100 people with ropes, one rope each person, and you have 100 of them in your hand, right? The closer they approach, the more the ropes fan out. Yeah. And if these people are infinity, where mathematicians send you at infinity, well, you see them all, almost on the same coaxial. It's like a single rope. They're all in front of you. They're no longer to the sides.
Are atoms like knots pulling the ropes around with them? Are they more like beads on a string, or do they move in some other fashion?
Well, they do move like a bead on an abacus. They do move. They slide along the rope. That's one issue.
But they're also knots.
They're knots. I think of them as knots as well. Remember, it's a place where the ropes converge, and one branches out and forms the electron shell or membrane, and the other one goes in and forms the proton star. So in that sense, they're knots. You can also think of a neutron as knots. At least I do. Not everybody agrees that vouches for the rope model. There are different opinions on this as well, different theories. My version is that the neutron is a convergence of ropes, and the perimeter of that neutron is more or less where the electron shell would be on a hydrogen atom. That's why the neutron more or less weighs as much as a hydrogen atom.
If gravity is tension, how do we get attraction? Why do larger objects win the tug of war?
Well, because it's got more ropes, more atoms.
Well, it doesn't have more ropes. They have the same amount of ropes.
No, but I mean, it has more atoms. Therefore, if you take two objects, here you have two objects, okay, two balls, okay? And this one's lighter, this one's heavier, so this one's got more matter. In other words, this one has got more hydrogen atoms. Let's call that the unit of matter. So this one, whether it's got carbon or nitrogen or whatever, it doesn't matter. What we're saying is, because this one weighs more than this one's made out of sponginess, right? This one doesn't weigh as much, so this one doesn't have as many hydrogen atoms in it as this one. This one has more hydrogen atoms.
So if these two were in space.
So if these two guys are in space, this one's going to win the tug of war against this one. In other words, because first, this one's pulled by every atom in the universe, so is this one. So that's what keeps them out there, with respect to all other atoms. But why does this one approach that one more than this one approaches? This one moves that one in that direction as well, but this one moves in this direction, covers more ground. Okay, why? Because, if you have an ant and an elephant, well, hopefully the ant falls towards the elephant, not the elephant towards the ant. Poor little ant.
The question is why?
Okay.
Why does the ant come towards the elephant?
Because this guy has more what we call inertia. And what's the inertia? Inertia is a measure of how much matter it's made out of. It's got it weighs more on the earth, for example, right? You got the elephant, you got the ant. The guy that's going to move is the ant, not the elephant. Okay, so why? Because he's got more matter. And all the ropes, all the atoms that make up the ant are tied to all the atoms that make up the elephant. But, it's even though the ant is also pulling on the elephant, like, you're pulling on the earth whenever the earth pulls on you, but the earth has a lot more atoms.
I think
and so you fall towards the earth, not the earth so much towards you.
It's actually a tricky question because it implies something else. If the elephant and the ant were the only two objects, assuming it doesn't matter if they're single pieces or made of many atoms, if you just had an elephant and an ant and no other matter, you couldn't tell if one is pulled to you couldn't tell if the ant is pulled to the elephant. The only reason the only reason you could see that is because you have all this other matter in the universe with which to compare it to. You see,
you're tied down. You're tied down.
Yeah, but the elephant is here and the ant is here.
Yeah.
With respect to the rest of the universe. If there was nothing else there, then these two would just come together and you wouldn't even see the elephant staying there, for example.
Yeah, and that's what Mach.
It's a weird.
It's got to do with two things. One is with Newton's bucket, the fact that you tie a bucket to a string and full of water, and you rotate it. Well, the water goes up the sides of the pail, and you say, what's pulling it there? Why doesn't it stay level? Well, it's all the stars that are pulling on it, and that's known today as Mach's principle. The stars are pulling on you. Otherwise, you wouldn't notice the difference between the elephant and the ant. The only reason is the elephant is anchored by all the stars in the universe, aside from the earth.
So there's no gravity in line stuck of atoms. I guess we're talking about a stack of atoms. If you have a row of atoms, there's no gravity there?
With respect to the object that you're measuring gravity against, yeah. In other words, if all the atoms are lined up, then all you have is the last atom is the only one pulling on one atom here.
Well, they're all...
And all the other ones that are in between, that are on the same axis, they're irrelevant. They're irrelevant, like I showed in the picture of the tug of war between Andy and Bob. And then you have, what's his name, Charlie. He comes in, he just holds the rope. They don't feel him. One guy's pulling on the other guy, and Charlie is irrelevant. The only way that Charlie can become relevant, the only way he can pull on both of them, because either he pulls with Bob or he pulls with Andy. But the only way he can pull on both of them is if he comes out of alignment. He brings the rope out of alignment. In fact, I do it with a rubber band. See, right now it's these two fingers, but now my son is going to pull that out of alignment. If you just hold just hold it first.
Yeah, I'm holding it.
But you're pulling me down. See, if he holds it, I don't feel him at all. I'm still feeling my two fingers, but you pull it out of alignment now. Now I feel him. And you can do this at home, always in the presence of a trained relativist. Okay, he'll show you that the only way you can feel the force of pull is if he goes out of alignment.
Let's talk about three atoms, which is one of my favorite situations. If you have three atoms in space, no other
three atoms
objects.
Yeah.
Why does one? I mean, would they all come together?
No. No. Again, it's very difficult because again we've got matter. All the stars, etc., that are pulling on the three atoms. Yeah, but another situation is God comes in there and wipes out all the atoms in the universe. He only created three atoms. We have a problem there because the only way you're going to get that tension is if they rotate. And rotate is only when you have matter out there. It's a situation that you cannot really reproduce. You can try to visualize it, but you're also making a lot of assumptions there, saying that you already have Mach's principle working there, that all the stars are pulling on those three atoms. You can't do it with just three atoms alone. God would go crazy trying to create just three atoms and having them do something. All you can do is try to simulate it and say, look, what happens with three atoms? And all I can tell you is the following, that if all three atoms are on the same, put your finger there, again, in the sun. If they're on the same axis, I don't feel his hand at all. The only way I can feel it is if he goes out of alignment. Then I can feel it. And that's what happens when you have a row of atoms with respect to one atom at the far end of another object. all those atoms are irrelevant. The only one that is relevant, the one on the ends. And the only way you can get to feel the other atoms is by approaching, shortening the distance, in which case now those atoms fall out of alignment. In other words, the ropes with respect to the other object are acting independently.
Yes,
they're not on the same axis.
The fanning effect.
The fanning out.
If you have a fanning out, then you have more and more of these guys not on the same line, so now all of a sudden they're felt?
Yeah, they're felt because suddenly this one's acting independently. It's the same thing as this.
Yeah.
The only way I can feel you is if you go out of alignment. Then I can feel that finger. Otherwise, if he's just holding there, you don't feel him. And again, do it at home. Take a rubber band or a string and just pull your hands, one against the other. Just tension. And you'll feel one hand with respect to the other. The only way you're going to feel the atoms in the center if they go out of alignment. And that's what gravity is.
Ooh. Got a lot of text here. Keep talking. You gotta
read all that.
Talking about definitions. Well, the problem that I always see with definitions that's hard for people to get their head around is when you have to define words to explain something. You don't just define words in a vacuum. Like here, Hippie Smokes is defining the word real from earlier, that which you can imagine or that which you can think of. But in a vacuum, that doesn't really give you anything unless you're actually going to use the word real in a scientific explanation.
Well, a lot of that has to do with preserving your religion, because people have these sometimes subconscious, but they have this protection. They have some beliefs or some theories. And they feel that those theories are threatened when a new definition comes in. And so there's a protectionist issue there where people say, well, no, I like the definition of ordinary speech. That's the one I've always used, the one I'm comfortable with, because it protects your religion. And you got to challenge is what Al Hazen said in the 10th century. He said, the true scientist begins by attacking everything he believes. He begins there. He questions. He acts as an enemy of everything he believes, and that's what you should do. So accept the definition first, the new definition, and apply it to yourself. And it's going to be uncomfortable. You're gonna lose a lot of your ideas or beliefs and theories or whatever. And it's challenging because you're saying, look, I'm going to attack my beliefs. Let's see, I'm going to act as my own devil's advocate.
Yeah. Where can I destroy my own theory? And
the way you do it is by applying a definition that is uncomfortable. And there are not that many critical definitions. For the foundations of physics, I have like 8 definitions, maybe 10, I don't remember now. But it's object, exist, location, distance. There's like 10 of them. And those forms the foundations of physics. And the difference is that they don't mean the same thing as in ordinary speech. And I had to do that because it's the malleability, the fact that you can mold them. That's what prevents us from understanding how the universe works. And once you define those words, at least you can talk consistently. And yeah, that offends people because suddenly their religion is threatened. They say, "Oh, hold it, this affects my religion." Yeah, it does. And so you got to apply it to yourself. You got to whip yourself. Flog. make sure you're comfortable with your theories.
There's this notion that Hippie Smokes brings up that kind of makes me think of, back to the topic of patterns. When we're talking about a pattern, we're not talking about something that exists because it doesn't have location. But philosophy talks a lot about behaviors and patterns, and you can't really talk about a pattern or a concept such as love being existing. But what could you talk about? Like when you notice a pattern in nature, for example, like extinction, for example.
Then it's happening. Then you're talking about a happening, and you can't say that a happening exists.
Yeah, that's the thing. But then what word would you use instead of exist?
Well,
It is, or what?
remember that philosophy deals with concepts first, and then it deals with reasons and purposes. The word exist does not fit into any of those contexts. So you can't use the word exist in philosophy.
But then what would you use?
Well, you use other words. But I mean, you can't use the word exist because the word exist is exclusive of physics. And in philosophy, we explain reasons and purposes. For example, why someone did something, right? It could be a crazy guy who killed people out there. Okay, why did he do it? Why did he commit suicide? Why did he go to China? You know, you ask a why question, and it's a why not like a cause or mechanism, but you're referring to purpose and reason. And what's the purpose of using the word exist in that context? That's what you got to come up with. You got to come up with an example where you can use the word exist in the context.
No, he's not trying to use the word exist.
No, but I'm saying this is the challenge. Okay, this is what I'm throwing for those who have out there this idea in their minds. Try to apply the word exist in the context of purpose and reason.
Yeah,
come up with a.
But that's why we're trying to invent a new word.
Okay, all I'm saying is if you can't do it, then you can't use the word exist in that context in philosophy. Philosophy is not the science of existence.
Okay, this begs the question why Mother Nature prefers more pull than less.
More pull?
I guess we're talking about gravity?
I don't know. Not clear. Hey, I know that guy. Go up a little bit. What did he say?
He's just talking to the people here.
When he says he means scientific, yeah.
Yeah, we're not using the word exist, we're using the word real.
Yeah, but real and exist are synonyms.
But he's saying they're not synonyms, because real is that which you can imagine, exist is that which has location.
No, real is also that which has location. There is
he's changing the definition.
Yeah, but then what's the context? What's the context?
Again, a pattern in reality. For example, love. Love doesn't exist because it has no location. It's just a concept. But it's a pattern that we've observed in philosophy. Yeah,
but you can say that, but when you say that love is real, what you're saying in a roundabout way is love exists.
No. Yes, that's the thing. We have to use a different word because we can't use exist.
Right, but
we have to use a new word for a behavior that we notice in nature.
Okay, but this is my question. The question is, when we say in philosophy, not in ordinary speech now, we're looking at science. Science is divided into two branches, physics and philosophy. And under the philosophy branch, we say love is real. Let's assume that, okay? What is the context? What do we really mean when we say love is real?
We're talking about
you're saying
pattern.
Love exists.
No, we're talking about the pattern that we've observed in human nature.
Then why don't you say, well, it's the pattern I observed in nature and saying love is real? Because love is real means love exists.
Well, it depends on how you define it. No, unless you define the word real.
Yeah, you got to
like we're talking about real concepts versus unreal concepts, I guess, because an unreal concept would be things that we haven't observed in nature, I assume.
Yeah, but again, you got to define the word real very precisely. And once we got that, we know what we're talking about.
Said that which we can imagine.
Yeah, but
needs more investigation.
Yeah, yeah, you can. The word real, the word is a synonym of exist, and both belong to physics.
Unless you define it otherwise.
Well,
it's like the word rational, which you separated from logical.
Yeah.
Which are synonyms in ordinary speech.
Yeah, to some degree they are. They're not even complete synonyms in ordinary speech. But rational means, again, we refer primarily to theories. And the number one there is that you can't move concepts. If you move concepts, you're an irrational individual. He says, I'm too offensive with that, so we say it's an irrational theory.
I mean, it's just more logical to talk like that. Going back to a really earlier question, how are new stars formed? We never really answered that. How is a new star formed? Because we talked about a star exploding, turning into an iron ball, but how is a new star ignited?
No, that's the Nebular Hypothesis. I have no problem with it. You have a cloud of gas and debris, atoms, iron, whatever was spat out by a supernova or a nova, and you have this cloud of gas. And this cloud of gas begins to rotate. Why? Because, again, gravity forces it to go into these circles like a galaxy, more or less, or like a skater. So they begins to turn, and gravity pulls every one of those atoms towards a center. Once it gets there, it forms this cloud of gas, which we call a star or a protostar. And it eventually, gravity pulls it together more and more until it becomes almost a perfectly round sphere. And at some point, because of that pressure, it starts igniting. What does igniting mean? It means that now it radiates. In other words, it has a high frequency. The ropes are torqued to a high extent. Okay, so you have many links and short links. We call that high frequency, and you get into such high frequency like X-rays and gamma rays, and that's what comes out of those ropes. And that's the signal. Those vibrations, those torsions, are what we receive here on Earth. We call that the sun. Okay, but what I'm saying is, when you compress that, you have pressure, and that pressure inside the center of the sun forces that high frequency
to shoot out
through every one of the ropes in the universe that's connected to that sun, to that star. So no problem with the nebular hypothesis. The only difference here is that for planets, a planet was a star that was captured by a star like our sun. So any other planet out there in the universe is just a dead sun, a dead star. That was captured.
Is our sun going to turn into a rock?
Yeah. Our sun...
I guess it already is a rock in the middle.
Well, I think there's what needs to be studied a little more. I haven't done great research on that, but you have stars which are very big, Antares and so on, they're humongous, and they're eventually going to turn into supernovas. Others are just going to be novas. So there's novas and supernovas. Our sun is going to be a nova, not a supernova. And so you get different results from those agglomerations of matter, which is what a star is.
Can you do an animation of what happens to a magnet's threads when you spin them?
I do have an animation. In fact, let's see, maybe I can.
Spinning magnets seem to produce some odd phenomena, and I'm curious about what the threads are doing.
Let's see. Well, here's one. Let's see if I can get it in here. Give me a second here. I'll get you.
Juggle while you do that?
No. Give me a second.
Holy crap! That's a lot of gifts.
Yeah.
We got a library open, people. We got a lot of folders here.
Oh, no, it's over here.
Thousands of folders of gifts made throughout the ages.
Well, where is it?
We got kangaroo, God, gravity, magnet 1, 2, and 3. Oh, okay, dude, how many are in here?
Okay, here you'll see. Whoa, moved the wrong guy. Let me get that. Here's an animation, gives you a feeling for it. Okay, you see the threads during push and pull, and what you see here is if you turn it sideways, nothing changes. You still have red against blue or north against south, but when you turn it 180 degrees, now you have push. They push each other away. Okay, look at it one more time. You have red against blue, and they're going in the same direction. They're going clockwise in that case. Here you're also going clockwise. And now you're going to have one of them going counterclockwise against clockwise. And they push each other away.
The rope's whipping each
other. They hit each other away.
Slapping, high-fiving.
Yeah, essentially that's the mechanism. And one of the problems people have, and this has to be clarified because this is where people have a problem with this, okay? And it's that they say, hold it. The threads go through each other, and here they're not going through each other. They're hitting each other or they're pulling on each other. And that's where the problem comes in. The key issue is aggregation or agglomeration or however you want to say it. You can't see an atom. But you can see a table. And you say, why can I see the table if it's made out of things which are invisible? the key issue is aggregation, agglomeration. You put a whole bunch of atoms together, you can see the object. We can see the object. We can see a table because it's a bunch of atoms together. But if I take that table apart out there in the universe, right, one atom at a time, blah, 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 and I have a gazillion atoms out there, I can't see any of them. And this is the same thing with the thread. The thread you cannot see, obviously, it's much smaller than an atom. We can't see an atom, much less can you see a thread. What happens? The thread, at its level, it doesn't have the property of touch, and it doesn't have the property where you can see it. But what happens? If you put a bunch of threads together, like in the case of a magnet, where you have a wall of threads, that's when they acquire the property of touch that we have in our macro world. This is a key point that people have a lot of trouble understanding, because they're so used to our macro world where we say, well, you can either see it and touch it or you can't. It's black or white. That's not the case in the Mother Nature's subatomic world, where the thread acquires tangibility and visibility not, but tangibility only with agglomeration, with aggregation, with many threads working as a wall. Okay, so you need to understand that to grasp the notion of why the thread and the rope are invisible and intangible, but they become visible and tangible when you have many of them, just like with the atom. That's an important key point that you really got to get through your head in order to understand the rope model.
Going back to magnetism, not just the thread spinning, but the magnet spinning too. Why do spinning magnets help produce electricity?
Well, that requires a whole show. We'll skip that question.
That's too many emotions.
Yeah, no, because you first have to understand what like you have a floating magnet, for example. Why does that magnet float? There's a lot of issues.
That's another thing when we're talking about the LHC thing with all the magnetism going down to a fine point. That's just a billion ropes, threads.
Yeah, what you have. One of these I worked with an accelerator known as an implanter. An implanter works at the kilo electron volt. These guys work at the giga electron volt. That's the only difference. It's a question of power, how much strength. But this is the issue. They're all made in the same way. They have a long beam line, and around the beam line you have magnets. Okay, what is a magnet? Well, it's something that twirls threads around. So you're twirling threads. The guys on this side go this way. The guys on this side go that way. And so they push anything in between. They squeeze it, and they do it from all sides. You have these quadrupoles, or maybe even more. You have magnets all around.
It's a tunnel.
Yeah, and so it pushes all the beam or whatever goes in there, pushes it inwards into a pencil. Okay, and that pencil is what, in the case of an accelerator, right? What you have is electricity, essentially. What is electricity? Under the rope model, all these atoms are connected. There is no electron bead that goes from beginning to end. It's just something that's torquing inside the beam line. And what the magnets on the outside do is crunch that into a pencil-like shape, and it's twirling. And what they do, they have one going in one direction, the other one counterclockwise, right? And what they do, they point these two beams, right, which are just twirling electron shells, and they point them at each other, and it's like pointing two drills against each other. So one's going this way, the other guy going that way, and you have all these sparks, and that's what they're observing in their bubble chambers or in their gas chambers.
Have you heard about the storm on Neptune, the reverse direction of movement?
No.
Storm on Neptune, stormy on Neptune.
No. There's all kinds of activity going on in the solar system in every planet. I mean, we had what was it? This Schumacher comet that fell into Jupiter. Finally, it was going around, and finally Jupiter caught it, and fell into it when they filmed all that great show. It just swallowed it. Jupiter, the god, he swallowed this comet.
I think we're running out of questions, but it's coming down to, I guess we're back to exist. Does fire exist? If fire has shape, do chemical reactions exist?
Fire is a concept, remember. Fire is combustion.
What about chemical reactions?
Well, again, it's if it's a reaction, it's a happening. It's an event. It's a phenomenon. Phenomenon don't exist. Phenomena don't exist.
What's the other word we use if we're not using exist?
We don't use
what do we use for phenomena?
It's a behavior. So you don't say a behavior exists. Not in physics.
Not in
That's
physics.
okay
Philosophy.
in philosophy.
Philosophy. What
No,
do we use?
not in well in psychology and psychiatry. You can say that. Well, his behavior exists. We can't say that in science.
But then what would we
That's
say?
ordinary. Well, you don't use the word exist or real. You just say, this is the behavior.
This is the behavior that we've.
This is how he behaves.
Or this is a behavior that pattern that we've noticed. But it does.
Yeah, let me give you an analogy so that it puts it in the proper context. We don't say the orbit of Jupiter. We say Jupiter orbits. That's the way you say it in physics.
Yeah.
And this is similar, very similar. You don't say the behavior exists.
Or
no,
it's
you
real.
say he behaves this way.
Yeah.
So you got to change your language when you talk in science. In ordinary speech, we use the word exists in many ways, and we don't care. But if you're going to talk philosophy, if you're going to talk science, physics, you got to use the proper language. You can't say the behavior exists. You say he behaves this
happening.
way.
It's a happening.
Yeah.
You can't really talk about a chemical reaction existing or being real or any of that. It's just a happening. It's a behavior that we've noticed, but the objects are what are real or exist.
That's one. The other one is you got to use the correct language. That's why language is important. People don't give importance in language. Say, "Oh, you're doing semantics, Bill." Yeah, it's semantics, but science is semantics. We have to communicate our mechanisms. We have to communicate our ideas, our explanations, our theories. That's why science is 100% semantics. You got to get the semantics right.
Have you ever made an animation of a cylindrical magnet?
No, I haven't done that. I want to do that. Also, a ball. Yeah.
I guess it would be down to a fine point in the center.
No, because we got these mapped. By the way, we do have. I haven't done it, but they have them mapped. The typical magnet is the bar magnet, the squarish, rectangular magnet. But they've mapped the magnetic field of a ball, which is the Earth. The Earth has that, more or less the ball-shaped magnetic field. And they also done it with cylinders. So it's a question of getting the pattern and just replacing the lines of force, Faraday's lines of force, replacing them with threads, with physical threads. Those are physical threads, for else you're putting spirits in that same region. If the thread is going to cause a force, there had better be something in there. Otherwise, you're introducing spirits in it, angels.
How does a Tesla coil magnify an electromagnetic field, for lack of a better term? How do they
you're putting
the
more
thing
atom.
go in?
You're putting more. If you have a coil, and now you're gonna, not a Tesla coil especially, but any coil, and because I think Faraday already did that, and you put iron in there, it increases the magnetic field. Why? Because what you did is put more atoms in there that are now, the atoms are aligned. Okay, they're aligned with the magnetic field, and all you did is just put more atoms, meaning you have more threads in there moving around. That's why it's increased. No, there's no mystery to it under the rope model.
How would all the atoms that form a storm? Oh, I guess we're talking about the pole shifting of Neptune, was it?
Well, no. I think the poles might reverse. Like I think they say like 26 million years. The Earth turns around.
Dark storm on Neptune reverses direction, possibly shedding a fragment of. I guess it's a NASA.gov article.
Yeah. Okay, it's possible. Those are specific questions. Of something that happened in the solar system. You have all kinds of activity. You have some volcanic activity out here and there.
How well do you speak and understand German? Grüße aus Speyer.
Oh, great, yeah.
Behavior is an alternative to exist in philosophy.
Okay, now starts the Spanish class. ¿De qué vamos a hablar ahora?
I hope you two see that this has not been resolved. It kind of has been resolved in the sense that we don't say phenomena are real or phenomena exist. We would just talk about the phenomenon itself. It's like what Bill said about the orbit of planet. You don't say there is an orbit or Mars is orbit.
Orbit cannot be the noun, in a sentence. You got to use the object. In physics, it would be Jupiter orbits. Orbits is what it's doing. And in the case of exists, the same thing for philosophy. You don't say love. The behavior exists or love exists. You say he is doing love. He is doing this behavior. You would put it in that term. You put the noun first and then the verb, which is typically what people say exists. You put it as the verb. You put it as the action. So you don't say love exists.
Nounifying.
Yeah, because then you're making love into a noun, and love is not a noun for the purposes of science. Only in ordinary speech is love a noun, intelligence a noun. In science, those are verbs, and you can't put verb as a noun in science. That's the irrational part of language that we have today.
How would all the atoms that form a storm the size of a planet can suddenly reverse 180 degrees in the rope hypothesis? I guess we're talking about pole shifting. They talk about that
well. Remember, the only difference between the north and the south pole of a magnet, the threads come into the south pole on the top part, right? Well, on both, really through the end, but they go in opposite directions. Like one is clockwise, the other one is counterclockwise. But they go into the south pole, they come out of the north pole. If you want to reverse polarity, let's assume by some external mechanism you want to change polarities, I'm sure you can do that, and all you're doing is just changing the direction of the threads in the opposite direction. For example, if you have a small magnet in a big presence of a big magnet, that big magnet, because it's much more powerful, can move the threads maybe in the opposite direction. And a case in point is an iron filing. Okay. Iron filing, if you take it doesn't have any magnetism. But you put it in a magnetic field, like close to a magnet, and suddenly it increases the magnetic field of that magnet, because the magnetic field of the magnet started moving the threads around of the iron filing. It magnetized the iron filing. What direction? In the direction in which the magnetic field was flowing. But you put that whole system now in the presence of a much bigger magnet, the Earth. And let's say it's going in the opposite direction. It's going to overrule that and force the threads to go in the opposite direction. Because it just aligns every atom to move in the opposite direction. So you can change the magnetic field from north to south, south to north, simply by putting it into a situation which a bigger magnet or a much stronger magnetic field has an influence over it.
Are you willing to answer questions which are not directly related to physics?
Well, depending what. I don't know. Yeah, sure, whatever.
I guess extinction would fall under that category.
Yeah, extinction, fair game.
You didn't even talk about other animals' extinction. You just talked about human extinction, didn't you?
Yeah, in general. But, like I always say, you got to do Extinction 101 before you do Extinction 102. Mm-hmm. 102 is human extinction. 101 is past extinctions, the ones we've certified already. We see those bones in the rock, we say, well, these animals are no longer around, and we got to explain that first. We got to have a mechanism for extinct animals. Then we can apply that, whatever theory you come up with, mechanism, you can apply that to man.
Are there any philosophers that you can recommend?
Yeah, my son here. He's a great philosopher.
Explain the rice experiment that results in love improving the lifespan. Oh, I've heard of that one, where they take, I don't know how true it is, but it's where you take two plants. I guess it was grown with rice. I wasn't sure.
And you love one more than the other?
Yeah, you give one, you tell one that you love it and whatnot.
Oh.
Yeah. that's a non-belief, right?
Well, I don't know. Maybe I'd have to find out, but I don't do philosophy, by the way. I'm not interested in that subject at all. I do a lot of history, but I don't put it on my channel. In general, I do that. That's my hobby, and I stay away from it because it takes too much of my time.
So why did Napoleon go to Waterloo? You never answered that one.
I'm still working on why Caesar went to England.
We're running out of questions. Yeah, bring back morons. I have a question. What does the edge of the universe look like? Of the matter in the universe look like?
I always say that the edge of the universe, okay, the edge of the universe is magnetism. It's got to have threads sweeping around. So if you want to know what the edge of the universe looks like, just go out outside one night, and there's got to be a magnetic field that you can't see. But if you had God's eyes, you would see this magnetic field surrounding the earth. That's what the edge of the universe looks like, a magnetic field on the last bit of matter out there.
I mean, but it'd be weird because if the swinging of the threads of the magnetic fields works by centrifugal force, which is what we're implying essentially.
Centrifugal.
Right? If you swing a thing around, the reason it
No, because gravity only has an effect on the atoms that from where the field comes out of. So it doesn't have an effect on the field like in mathematical physics where they say that gravity bends light. Not true. Only when you drink too much, then it does bend light. Your light starts bending in one direction.
I guess we're running out of questions. Do you have any questions for them?
No, but we'll see you in 1 year. I'll see you in the year 2021. Okay, folks, we'll call it end of the year, and we'll see you next year. So you got to wait 1 year to see me again, okay? Next year, we'll see you again, and hopefully you have a grand New Year's. Despite the fact that this was the lost years, this corona stuff or whatever, or whether it's true or not, the economic effects were real, no doubt about that. So we'll see what happens next year.
Real or the economic effects existed?
Yeah, they existed. We'll see you next year, folks. Bye-bye.
All right, guys, have a good one.
Bye.